Hey, welcome to Lesson 13.6, the Law of Cosines. Okay, so in the prior lesson, we learned about the law of sines, and we learned that you can use the law of sines on any kind of triangle, not just right triangles, and that was really the limitation of the sine, cosine, and tangent ratios. And so we knew that there was a prerequisite to use the law of sines. We had to know an angle side pair where we knew both measurements. So an angle and the side across from it where we either were given it or could find it very easily with like the triangle sum theorem. But what about if you have a non-right triangle and you don't meet that criteria? Well, then what? So are we just out of luck? Well, it turns out no, we're not out of luck. We have another law, and this is called the law of cosines. And again, this is something we learned in Geometry B, so this may come back to you pretty quickly. But let's take a look at our learning goals. So we're going to use the law of cosines to find side lengths and angle measures of a triangle. And secondly, we're going to use this thing called Heron's formula to find the area of a triangle. So you probably know one way to find an area of a triangle, and you think, why would we need another? We know area equals 1/2 times base times height. Well, you may remember it's sometimes difficult to find the height of a triangle. So this is going to give us an opportunity to find area with different parts of a triangle now. So the law of sines was really pretty simple to use. It was simple to remember. It basically was like the sine of any angle in a triangle over the side across from it. And we could take any of those ratios, any two of them in a triangle, set them equal to each other, and if we knew enough information, solve for a missing part, angle or side. Well, if we didn't have that, meet that criteria, this was sort of our backup plan, is the law of cosines. And the reason why we kind of would say it's a backup plan, although you might find it pretty easy to use after we kind of get used to it, but because it tends to be harder to remember. It's fairly complicated. And maybe it's complicated by the fact that when they state the law of cosines, they give you 3 different versions of it, which are sort of unnecessary. And so for me, I sort of just eliminate these right here. I sort of pretend like only one law of cosines exists. So I'm going to get rid of these. You can cross them out if you want, because the letters are really, are sort of arbitrary. They don't, not every triangle is going to be a triangle called ABC. So really it just matters what the law says, and we can adapt it to our particular triangle and whatever parts we're trying to find. So I like to look at this one, and I say that this is the law of cosines. And what it says is this. It says that this side C squared is equal to A squared plus B squared, which is the other two sides squared, minus 2 times A times B times the cosine of C. So basically, sounds kind of complicated. It's saying that any side in a triangle squared is equal to the sum of the squares of the other two sides minus 2 times the product of those other two sides times the cosine of the angle across from the side you're trying to find. Okay, so it does sound complicated, but you may see a part in there that looks kind of familiar to you, and in fact, it is based on Pythagorean's theorem. And we know Pythagorean's theorem, this part right here, only works for right triangles, right? So if this was a right triangle, we would know that the c squared, which is the hypotenuse squared, would equal the sum of the squares of the two legs. But because if we don't have a right triangle, we don't really have hypotenuses and legs. But what this does is this minus 2, this part down here at the end, this minus 2ab cosine of c, that part adjusts just for the fact that we don't have a right triangle, or we may not have a right triangle, because as I said before, you can really use law of sines and cosines for any triangles. It's just probably better to use the trig ratios for your right triangles. But if you have an acute triangle, this minus 2ab cosine of c will adjust for the fact that your largest angle is less than 90 degrees. If you have an obtuse triangle, this part adjusts for the fact that you have an angle in your triangle that's larger than 90 degrees. So it turns out that it will adjust and make a side that would be longer than what a hypotenuse would be if it's across from an obtuse angle, and vice versa for the acute. So, really it doesn't matter, what letters you use to describe it. What it means is this, that if you're trying to find a side, you need to know the other two sides, and you need to know the angle across from the side you're trying to find. Because as I hope you can see is really clear here, that this is C and the angle is C. So this is the angle across from the side. And then, of course, these are the other two sides. The A and the B are the other two sides that, so to use this, you have to have, basically, the criteria to use it. To find a side, you have to know two sides and the included angle. So up in this triangle, it would mean that you'd have to know, for instance, say side A and side B and angle C. So you have to kind of have the side angle side condition. And again, I really don't like to remember like side angle side and all that. And so what I do is I think about it, can I use the law of sines? And if I can't, well, then this is sort of my backup plan. So I always think law of sines first. And if I can't use it, then I know my only choice is to go to the law of cosines. Let's go ahead and take a look at an example and we'll kind of put this into practice. Okay, so I'm asked to solve these triangles, and again the directions are to round sides to the nearest tenth and angles to the nearest degree. And I don't have a drawing to go with this, which is okay. That's fine if I don't have a drawing, because all I have to do is take what information I have and label it on this triangle. That I just created my own triangle, and you know I'm going to call it start labeling like this: A, B, and C. So the angle that they gave me is this angle, and I'm going to say it's 32.2 degrees. So I tried to pick one that I thought looked most like that measure, and labeled it. And then they give me side A, which would be across from angle A, so that would be over here. And it is 8 units long. And they give me B, which is, again, of course, across from angle B. So that would be this side right here. And so we can kind of get an idea of what this looks like. So we have met the criteria that we need. We have the two sides and the included angle. And so we can use the law of cosines. And also I could tell just by looking at it, I can't use law of sines. I don't have that angle side pair where I know both that I need. So I'm going to start off by calling this side C. And again, it doesn't have to be called C because your triangle might be like triangle XYZ. But I'm looking to find side C, so I'll call that C. So I know that that side squared is got to be equal to the sum of the squares of the two sides I know. So that means 8 squared and 5 squared, and you can put either one first, it doesn't matter. And then I'm going to subtract from that 2 times the product of those two sides. So this is just following the formula, times the cosine of the angle across from the side I'm trying to find. And that is the one angle that I do know. And that is the one that's 32.2 degrees. So it turns out that this isn't even an equation to solve. I mean, everything that we know is on the same side, and the thing that we want to know is by itself. So it's already set up to be solved very easily. And in fact, all we have to do is in one step in our calculator, we can put this whole thing in, figure out what it is, and then all we'll have to do is take the square root. Or we could even, if we wanted to, be really bold about it, we could do it all in one step, and we could do this. Take the square root of this whole thing in parentheses, but let's, to be for safe, for the first time, we'll just go ahead and do it in some steps. So first we want to figure out what 8 squared plus 5 squared minus 2 times 8 times 5 times the cosine of 32.2 degrees is. So I'm going to pause the video, and you should pause the video and type that in your calculator and see what you get, and then write it down and tune back in. So this is what I got, and I wrote down all the digits that I could see on my calculator. 21.30454671, and of course it goes on and on and on. And so, but that's not actually my answer, because that's what C squared is, but we want to know what C is. So we're going to have to take the square root of both sides. So if I square root this number, I get approximately, and remember they wanted me to round to the nearest tenth, approximately 4.6. So that side absolutely makes sense here, because it's got to be, this looks, you know, the other two angles, I've got an obtuse angle, looks like, and another acute angle. So I've got to have a side that's definitely smaller. And actually I just noticed we probably should have flip-flopped these. It doesn't really matter, but I should have had these measurements be B and A. It should have been A, B, C like this, so that this side would have been the side that was 8 and this was 5. But notice this would have no effect at all on our calculation. But it makes more sense now to look at that that side that's across from the biggest angle is the side that's 8. And of course that would be the biggest side we can see now. So be careful when you're drawing your triangles. I guess they don't really have to depict, because I made this, you know, drawing myself. So I don't know that that's what the real triangle looks like. Anyway, so the side that I was trying to find, side C, is about 4.6. I know the other two sides because those were given. Side A was given as 8. Side B was given as 5. Angle C we knew was 32.2 degrees. And now we have 2 more angles to find. Well, if you wanted to try to use the law of cosines in the form that it's in to find an angle, that would actually be really difficult to do. Although we could do it because we have all 3 sides. And we'll look at a way later on in the lesson where we could actually find angles using the law of cosines. But for now, it might be smart just to go back to the law of sines, because we now have an angle side pair that we know both of. See, we know this angle side pair. We know the 4.6 and the 32.2. So I'm just going to go ahead and use the sine ratio. I'm going to say the sine of 32, I'm sorry, not the sine ratio, but the law of sines, over 4.6 is equal to the sine of, let's find angle B over 5. So I'm going to use this to find angle B first, and then we can go back and we'll use the triangle sum theorem to find angle A. So let's take a look at angle B. So to solve this, I'm going to do the cross products. So I'm going to multiply across, so that'll give me 5 times the sine of 32.2 degrees is equal to 4.6 times the sine of B. And then I'm going to divide both sides by 4.6, and when I do that on this right hand side, it basically just cancels the 4.6 out and leaves me with the sine of B. And on this side, when I take 5 and multiply it by the sine of 32.2 and divide it by 4.6, I get approximately 0.579, and that's equal to the sine of angle B. So my last step is to just undo that sine. I got to get B all by itself so I know what the angle is, so I have to get rid of the sine. I'll inverse sine, take the inverse on both sides, because that's how you undo the sine, is the inverse of it, which is the inverse sine. And go ahead and calculate the inverse sine. So the inverse sine of 0.579, and that is approximately 35.4, but they wanted us to round to the nearest degree, so that's about 35. So we're going to go with 35 degrees for angle B. But you know, I'm actually, when we're finding that, I think it's kind of worth going an extra decimal place to be more accurate. But they did ask us to go to the nearest degree here. So we'll go ahead and honor that request, and we'll say that angle B is 35 degrees. And so now to find the missing angle, I can take 180 degrees and subtract the 2 angles that I know that are 35 and 32.2, and I get 112.8 degrees. So let's turn the page and let's take a look at how we might use the law of cosines instead of the law of sines to find angles. Well, I mentioned earlier that we can also use the law of cosines to find angles, but that using the original law of cosines was very, very difficult to do. And maybe when we are together in class, I'll show you one of those where you have to go through the entire thing. But for now, I'm going to introduce you to another version, alternate version of the law of cosines that you probably won't find anywhere. I haven't had good luck searching that out, although I haven't looked in the last year or so. This is basically a formula that we wrote by taking the original law of cosines and solving it for the cosine of the angle. And this is what the process looked like when we came up with this. And actually, I have to give credit to a student, because I had a student quite a few years back that said, you know, why are we going through all of this to find angle measures every time? Why don't we just rewrite the formula so that it's tailored for angles? And I thought, well, that was brilliant, and we've used this formula ever since. But I'd like to show you where it comes from. Okay, so here's the one version of the law of cosines that I choose to use. And c squared equals a squared plus b squared minus 2ab cosine of c. So what my goal is I would like to have this solved so that I have the cosine of c all by itself. I want this thing all alone by itself. And here's what I'm going to do to get it that way. So I'm going to start off first by getting rid of the things that are around it. So I have a squared and b squared that are both being added on that side. So I'm going to undo those by subtracting those. So I'm going to subtract a squared from both sides. I'm also going to subtract b squared from both sides. And what that ends up giving me on the left-hand side here is c squared minus a squared minus b squared. And that equals negative 2ab cosine of c. And remember, I'm trying to get this part all by itself. So that was the first step I took. Okay, then the next step I said, okay, well, now I've got to get rid of this minus 2ab, and it's actually being multiplied by the cosine of c. So I know I undo multiplying by dividing. So I'm going to divide both sides by minus 2ab. So I did that over here, divide by minus 2ab, and now that basically goes over here and cancels out this stuff, and what's left is this formula. I've got the cosine of c left, and really it could be the cosine of any angle, is equal to c squared minus a squared minus b squared, all divided by negative 2 times a times b. So that's this formula that you see here. It just came from solving that formula to get the cosine of the angle all by itself. And the one thing to note with this, and once you kind of know this fact, it actually makes this formula really easy to memorize, is that this c here is the angle that's across from this c here. So that's the one thing that is real crucial here, is that whatever angle you're trying to find, you have to put the side across from it in the formula first. You have to call that side C, or whatever. That has to be the side across from the angle you're trying to find. And then the other two sides can go in either spot. So you can put, either one of the other two known sides in for A or B. And other than that, this formula is actually really easy to use. Now, this would actually find you the cosine of C, and we know then to get rid of that cosine, we'll have to use an inverse cosine to cancel out the cosine. So a final step in using this would be then to take the inverse cosine of both sides. So in order to use this, you can see that we would have to know all the side lengths. So in order to find angles with law of cosines, you need to have the side condition or know all three sides. So let's take a look at how we might incorporate this into a problem similar to the one we just did. Now, it's not really necessary to have a drawing to go with all of these. It might feel helpful to you if you want to draw one. Certainly you could draw one here to, just get an idea of what everything looks like. So maybe something like this. I had to make this a kind of a really extreme triangle because angle A had to be 173 degrees, so it was a really big angle in this triangle. I don't know the side across from that. I don't know A, and I know side B. It is 23, so let's say this one's 23. This would be angle B right here, and this would be angle C, and across from it would be 18. So something like this, but again, you don't really necessarily need a drawing. So the first thing we're going to do is find the missing side, because we need three sides. So we know how to use the law of cosines to do that. This is what it would look like. We would say we have the two sides, right? And we know the angle between them, so we've met that condition to use the law of cosines. So this time we're looking to find side A. So we'd say A squared is equal to, then we'd take the two sides, square them, put either one of them you want first, minus 2 times the product of those two sides. Again, either one can come first. Times the cosine of the angle that's across from the side I'm looking for, 173. So we can put all of this into our calculator and we'll find out what a squared is equal to. So I'm going to pause real quick and see if I can calculate that for you. And I got about 1,674.828214. And of course that's not the side length of the triangle, that'd be way too big. But I have to take the square root of that, and that would give me about 40.9. So that side length is about 40.9, and that makes sense because it has to definitely be the biggest side of the triangle. It's across from that big 173-degree angle. And so side A is about 40.9, and of course the other two sides were given. Side B was 23, and side C was 18. So we know those, but we don't know any angles except for angle A, which is 173. So now I have this angle side pair that I need for law of sines. I could use law of sines, but let's go ahead and use the law of cosines so that we can kind of get a feel for how that works, because in some situations we'll have to use this, as in the next example. Okay, so let's say we wanted to find the measure of angle B first. So we've got to use the law of cosine. Well, we could use the law of sines, but since we just talked about this new formula that we can use, the law of cosines version for angles, let's go ahead and find angle B. So we're going to go ahead and find angle B, and that means we're going to have to use the law of cosines in this way. So we'll say the cosine of angle B, since that's the one we're trying to find, is equal to, and now we want to take the side across from it to put in first. So that's going to be 23. So we'll say 23 squared minus the square of the other two sides. So we have 18 squared and 40.9 squared, and you can put either one first. Then on the bottom, we have a minus 2 times, and now the two sides that are going to go in the denominator are the two sides that we subtracted from 23 squared, and that's the 18 and the 40.9, because we only use, notice in the formula, you only use the side across from the angle you're trying to find one time. So that means I'm going to be using in the denominator the 18 and the 40.9. So you have to be careful, because you know at this point is where you would take the inverse cosine of both sides. But before you do that, let's go ahead and simplify, because there's a lot going on here in these in the denominator and the numerator. So it's just probably a good idea to figure out what these are equal to and then go from there. So I put the numerator in my calculator, 23 squared minus 18 squared minus 40.9 squared, and I got negative 1,467.81. And then I put the denominator in, and I got, let's see, negative 2 times 18 times 40.9. And I get a negative 1,472.4. So I know my last step is going to be to have to do the inverse cosine on both sides. So if I take the inverse cosine of this side, of course that's going to cancel out the cosine. If I take the inverse cosine of this side, I get angle B to be about 4.52526, and so on. And it's set to round to the nearest degree. Now I'm going to kind of stray from that a little bit, because when you're smack dab in the middle of an angle, to round that to 5 degrees, that's actually a big jump, especially as small as these angles are. So I'm going to go with 4.5 as that angle measure. So I'm going to say that angle B is 4.5. I decided to go 1 decimal place further than they asked for. So that's 4.5. Well, now that I know two of the angles, I can actually just take the two angles that I know away from 180, and that will give me the remaining angle. And that's about 2.5. So I feel better giving the decimals here and not making too big of a rounding error with that rounding to 5 degrees from 4.5. So that's how you use the law of cosines to find angles. And you really could have used the law of sines there to find that angle B, or even angle C if you'd rather have found that one first. But in the case of this next example, when you're given all three sides and no angles at all, you really have no choice but to use the law of cosines. So let's take a look at one more example of using this new formula for the law of cosines to find angle measures. So this time we're given a triangle, and we just know all three sides. The sides are 8, 9, and 7. Side A is 8, side 9, B is 9, and C is 7. So again, if you need to have a drawing of that, you certainly could just draw a triangle for reference. But that's just taking up space I need to work anyway, so I'm not gonna draw one this time. So I'm just gonna randomly pick an angle that I want to find first. So let's say I want to find angle A. So I could say the cosine of angle A. That's what I want to find, angle A, so I'm going to write the cosine of that equals. Well, that means the side I'm going to have to put in the law of cosines for angles version first is going to be the side across from the angle I'm looking to find, and that's side A. So I'm going to put the 8 in first, and then the other two sides can go in either spot. It doesn't really matter. So I put the 9 first, but you could put the 7 first, and then vice versa, flip them around. And then on the denominator, then I'd have -2 times the 9 and the 7. So again, just keep that in mind. You're only using the side across from the angle you're trying to find in just that one spot in the very first position. Otherwise, it's the other two sides. So now I'm going to figure out what the numerator of this fraction is. I'm going to go ahead and put that in my calculator. And so if I take 8 and square it, and I subtract 9 squared and 7 squared from it in either order, I get a -66. And for the denominator, I get a -126. Well, that's what the cosine of angle A is equal to. So if I wanted to figure out what -66 divided by -126 is, you can do that. But again, it's actually a pretty simple calculation to just go ahead and take the inverse cosine of both sides right now. And so when I do that, and let's see, that gives me a angle measure of about 58.4 degrees. And so they want me to round to the nearest degree. I'm not a real fan of that. I just feel like that, that's some big rounding error. But that's what they ask for. So we're going to go ahead and round it, and the nearest degree would be about 58 degrees. But technically it's like 58.4 degrees. But we're going to go ahead and list the angle A as 58 degrees because we're going to follow the instructions that say nearest degree for the angle. So what we're going to do is now we need two more angles. So we're not ready to use the triangle sum theorem yet. We need two to do that. So we're going to use this same thing again. And we're going to use it to this time find one of the other angles. So you pick whichever one you want to find. And I'm going to pick angle B. So if you want to do this separately from me, you can. But I will tell you that sometimes because of the rounding, if you pick a different angle to do than I do, then the rounding might affect what the other angle might be. So I'm going to go ahead and use the cosine of angle B. I'm going to do B. And that means I'm going to have to put the side across from it in first. And that means I'm going to be putting in 9 in my law of cosines first. So it'll be 9 squared minus 8 squared minus 7 squared, or you can flip the 8 and the 7 around, divided by -2 times 8 times 7. I'm going to figure out what this numerator is on my calculator. And that's -32, and then the denominator is -112, and my final step then to find the angle B is take the inverse cosine of both sides, and that's going to give me about 73.4 degrees, which would then round to 73 degrees. So we're going to go with the 73 again. Again, against my better judgment, I think those are big rounding errors, but that's what they ask us to do. So we're going to go ahead and round to the nearest degree, which is 73. And now we have two angles. We just have to find the third by subtracting the two that we know, the 58 and the 73. That leaves us with 49 degrees. Now, one thing to be just aware of, depending on the order of which way you find the angles, and the rounding issues. You might be off a tiny little bit, like you might be off by a degree, like one of your angles, if you find them in a different order than I do, might be 1 degree higher and your other one would be 1 degree lower. But as long as they add up to 180 at the end, and then those rounding errors, they sort of kind of even each other out. But to really be accurate, we really should be going to more like the tenths or the hundredths. So, in future applications of that, you'll probably be more accurate with them and go to more decimal places. Okay, let's go ahead and turn the page. So as a you try, instead of asking you to do this whole entire process, and as I told you, there's some kind of pitfalls there when you're finding all the angles, I'm going to ask that you just find one of these angles. So I'm going to ask you to pause the video, and I want you to find angle C. So I want you to find angle C, and then tune back in, and that's the only one we're going to find for this example. So pause the video now and find angle C using these 3 side lengths. So angle C should have been about 81 degrees. So for example 2, we're going to look at a real life example. So if a hiker travels at an average speed of 2.5 miles per hour, how long will it take him to travel from the cave to the waterfall? So there's this hiker, he's out walking around and he wants to know how long, if he's going at this rate, will it take him to go from the cave to the waterfall. So in other words, they're wanting to know what the length of this, and they're talking about how many miles that is, and then we can figure out with his pace how much time it'll actually take. So we want to know what the length of this distance is. We want to know what, let's call this x. So whenever we have a real life problem, we should always check to see if we can use the law of sines first. And we can't because, we have 2 sides, but we don't know the angles across from either one of those. And we know an angle, but we don't know the side across from that. That's exactly what we're trying to find. So we do have 2 sides and the included angle. So this is the situation here. We have this side, and we have this side, and we have the angle between them. This is the perfect situation to use law of cosines. So we can say that the side we're looking for, say we call it x. That's why it doesn't really matter what letters we use in the law of cosines, because, in this particular triangle, we might not call it c. So we'd say x squared, that side squared, is equal to the sum of the squares of the 2 sides we know. That's the 4 and the 3, so 4 squared plus 3 squared, minus 2 times the product of those 2 sides, times the cosine of the angle that's across from the side we're looking for. So this is the angle and it's the only angle that's actually given, so we're pretty safe, 71.7 degrees. So let's figure out what that entire thing is, and that's, let's see, 4 squared plus 3 squared minus 2 times 4 times 3 times the cosine of 71.7 degrees. And that turns out to be about 17.464. Now we're trying to find out what x is, not x squared. So we have to take the square root of both sides, and that's going to leave us with approximately a value of 4 point, they want it to the nearest, so we'll go say 4.2 miles we need to go. And so now if we want to find out how long that's going to take, so this length right here is about 4.2, and so if we're going 2.5 miles an hour, all we have to do is take that 4.2 miles, divide it by the rate that we're going at, which is 2.5 miles per hour, and that'll tell us how long. And so that 4.2 divided by 2.5 gives us approximately, and they want it to the nearest tenth of an hour, it's about approximately 1.68, so it's about 1.7 hours. And so that's how long it'll take to make that travel, that trek from the cave to the waterfall. We're going to leave example B as a you try in class. So we'll put you try in class because we have still one learning goal left to cover before the end of the class period. So we're going to put this as you try in class. So we'll come back to that when we meet again. But let's turn the page and look at our last learning goal. So our final learning goal is to apply Heron's formula. So where this actually comes from, you can feel free to look this up online. There's lots of information about where Heron's formula comes from. But basically, Heron's formula is a way of finding area of a triangle by not just knowing the three sides of the triangle. So you don't actually have to know the height. Now, normally when we find the area of a triangle, say I had this random triangle here, and say I knew that the base of this triangle was, say, 6. In order to actually find the area of this triangle, I would have to know the height from this side to the opposite vertice. And so I would actually have to know what this length is, this length inside the triangle. Well, oftentimes we don't know that, and the process to actually find that can be very difficult and sometimes impossible. So what Heron's formula says is if you just know the three sides of the triangle, this formula will find the area. And this is how it works. The area formula is found by taking the square root of s times s minus a times s minus b times s minus c. Well, what does this s mean? Well, the s actually is 1/2 of the perimeter of the triangle. That's what that means. The s is equal to half the perimeter. And so each of these little differences here mean the difference between each side and half of the perimeter. And so utilizing this, we can find area just with side lengths. Here's an example of that. So it says use Heron's formula to find the area of the triangle with the given side lengths and round to the nearest tenth. So the first thing I want to always do when I'm finding area using this formula is find the perimeter. So I'm going to start off with the perimeter, and I'm going to calculate that. So we can find the perimeter by adding these sides. And they add up to 15. So now I'm going to find half of that perimeter because that is what s is equal to. So half of the 15 would give me 7.5. So I know s is 7.5, so now I'm ready to use this formula. So the area is equal to the square root of s, which is 7.5, times 7.5 minus one of the sides, doesn't matter which one you put first, so I'll subtract the smallest one first, then times 7.5 minus another one of the sides, and finally 7.5 minus the third side. So we're just going to find out what all these differences are. We'll multiply all these numbers and then take the square root. So I have 7.5 times, well, 7.5 minus 3 is 4.5. 7.5 minus 5 is 2.5. And 7.5 minus 7 is 0.5. So now I can just go to my calculator, figure out what all that is, and take the square root of it. So 7.5 times 4.5 times 2.5 times 0.5 turns out to be 42.1875, and then all I have to do is take the square root of it, and that will be my area. So the square root of that is approximately 6.495. They want it to the nearest tenth, so 6.5, and because the units were given in feet, then my area is square feet. So 6.5 square feet. So we'll look at one more example, and then we'll designate this example B as another you try in class. So that we'll have these two problems, one from the prior page and this one, to come back to when we meet in class. So example A, a garden has a triangular flower bed with side measures of 2 yards, 6 yards, and 7 yards. What is the area of the flower bed to the nearest tenth of a square yard? Okay, so first step is find the perimeter and then take half of it. So the perimeter is the sum of the sides, and so these sides add up to 15 again. All that. Interesting coincidence. So that means the side, or the S is half of that, which is again 7.5. So this time our area is going to be equal to the square root of 7.5 times the difference between this S and each of the side lengths. So even if you want to do some of these calculations in your head, you certainly can do that. but I'm just going to write it all out since it's the first time we're using them to make sure you understand exactly where all these values are coming from. And so let's see, the difference between 7.5 and 2 is 5.5, and between 7.5 and 6 is 1.5, and between 7.5 and 7 is 0.5. So we'll figure out what all these multiply to together and take the square root. And that turns out to be 30.9375, and of course we have to take the square root of that, which gives me approximately, to the nearest tenth, 5.6, and my unit would be square yards. So there's the area of the triangular flower bed. Okay, so that's going to do it for today's lesson. And so when we meet again, we'll go back and look at any questions or concerns you might have on the law of cosines, and we'll also do the two in class you try. So I'll see you then.